Welcome, dear students. Question number 11, 2023, Probability and Statistics, paper CC 11. Question 11, obtain the maximum likelihood estimates of alpha and beta for the random sample x1, x2, xn drawn from an exponential population with probability density function, this f of x alpha beta equal to y0 e to the power minus beta bracket x minus alpha beta greater than 0 alpha less than equal to x less than equal to actually it is the less than infinity, not less than equal to. It is the wrong. This is the less than equal to. Less than infinity. For this probability density function small f, the total area under the curve equal to 1. So we determine y0, this constant, y0 constant, by integrating over the range, this alpha to infinity, this integration alpha to infinity y0 e to the power minus beta x minus alpha dx, this is equal to 1. So integrating, we get e to the power minus beta x minus alpha with respect to x, integrating with respect to x, so this minus 1 by beta. Limit alpha to infinity. Actually, this limit um, it should be put here some constant capital B, and limit capital B tends to infinity, and then this e to the power minus infinity tends to 0. So we get y0, this uh, this alpha put here x alpha, when x equal alpha e to the power 0, this is equal to 1. So we get y0 beta equal to 1. So y0 equal to beta. So the density function becomes this f of beta e to the power minus beta bracket x minus alpha for x greater than equal to alpha. The likelihood function L, actually this L is a function of alpha and beta. These two estimates of this parameter alpha and beta here. So for a sample of size n is the product of the individual densities provided that the every xi greater than alpha. So this pi I equal to 1 to n. This pi means this pi means this equals to actually beta e to the power minus beta bracket x1 minus alpha into beta e to the power minus beta bracket x2 minus alpha, and so on. This. So this for I equal to 1, we get this into, for I equal to 2, this summation for this product, this the capital pi, notation capital pi for the product of this. So e to the power beta, so beta to the power n, there are n terms, product of n terms, so beta to the power n, and this e to the power something into e to the power something, so we can add these powers of e to the power. So e to the power taking common minus beta summation x1 plus x2 plus x3 and dot xn, so summation xi minus alpha. This is the power, adding the all powers of e to the power this, so we get this. Now taking log to the base e on the both sides of the given above equation, so we get log L to the base e equal to n log beta to the base e. So this beta to the power n, so n log beta, this natural logarithm, minus, you can write this ln, simply ln log to the base e. You can write here simply ln, this minus beta into this taking logarithm to the base e, so cancel e, so we get this beta summation xi minus alpha. This is the log likelihood function of this L. Now we want to maximize log L function. Actually, you want to maximize L and hence log L also with respect to alpha and beta. So partial derivative del alpha of log L to the base E, because this log L is also a function of alpha and beta. Here n constant, xi constant, all xi is constant here. So del alpha of log L to the base E is this beta into summation of xi plus this alpha in terms for alpha, so n into beta. So we get with respect to alpha, partial derivative with respect to alpha. So here only alpha term is here. So we get only from this last term, third term, in beta. Now n is the sample size, positive, and beta is the scale parameter, beta is also positive. The above partial derivative, which can never vanish, this partial derivative can never vanish and is always positive as n beta is greater than 0. This means that the function log L to the base E is a strictly increasing function of alpha. So we cannot find out the maximizing log L by the partial derivative equating to 0. So we apply here another technique here. Hence we proceed to find the absolute maximum if it exists of the likelihood function L as follows. First we choose the fixed beta value of beta, but the sample values x's are also kept fixed. Then L function L is a function of alpha only. So from this L, this beta fixed and xi also fixed. So we get this function L, this equals to L beta to the power n exponential of this. So we get uh, L equal to beta to the power n e to the power minus beta summation xi into e to the power beta into n alpha from this relation. E to the power beta minus summation minus beta minus summation of xi and plus minus plus. So e to the power beta n alpha. So L function is this. Now we can write this equal to c into e to the power k alpha, because this c, actually c equal to beta to the power n e to the power minus beta summation I equal to 1 to n xi. So this equal to c, this greater than 0, and e to the power k alpha. Here k equal to beta n, k equal to beta n, also greater than 0, are some constants. So actually L is an exponential function. Clearly L will be globally maximum when alpha takes the maximum possible value. So from this graph, this exponential function, this maximum likelihood estimator, this alpha hat minimum of xi. So this exponential function L strictly increasing function, sorry, this is the exponential function. L will be globally maximum when alpha takes the maximum possible value. Now alpha less than equal to xi less than infinity. It is given that from the equation this alpha less than equal to x and less than infinity. So we get this. So alpha takes the maximum possible value. Alpha is this. So alpha actually alpha takes the less than equal to takes the minimum value of this. Minimum value, the maximum value of alpha is the minimum of these sample values x1, x2, xn. We say this minimum value is x star. So alpha takes the value x star. So substituting this x star in place of alpha, log L to the base E, we get the new function log L1 to the base E. Actually, this L1 is nothing, but we replace only the x star in place of alpha. So log L1 to the base E equal to n log beta to the base E minus beta summation xi minus x star. X star is the in place of alpha. And this, we note this x bar, this sample mean summation xi by n. So we can write summation xi equal to n into x bar. This summation runs from I equal to 1 to n. So this beta into n x bar minus n into x star, this taking common n log beta to the base e minus beta bracket x bar minus x star. This L1, log L1 is a function of beta only. So we we take derivative with respect to beta, not partial derivative. dd beta of log L1, because L1 is a function only depends on the single variable beta here only. In x star, x bar, all fixed quantities. So dd beta of this with respect to beta, taking derivative with respect to beta, here we got only get 1 by beta taking common n, and from this x bar minus x star. Now we want to get this log L1 maximize. So this first derivative equating 0, we find the value of beta. So this beta equal to 1 by x bar minus x star. Here we assume here x bar not equal to x star. Next, we find the second order derivative to check the minimum or maximum. So this equals to, we get next derivative, second derivative is this with respect to beta. So we get n for the 1 by beta is minus 1 by beta square. So n minus 1 by beta square. Obviously, both are positive. So this less than 0 for all beta. So obviously log L1 to the base e is relatively maximum for beta equal to 1 by whole divided by x bar minus x star. So now this beta, when beta is less than 1 by x bar minus x star, that is 1 by beta is greater than x bar minus x star. So first derivative is positive. So first derivative is positive. This means this dd beta of log L1, actually we get this dd beta of log L1 is this. So this 1 n into 1 by beta minus x bar minus x star. So this, when 1 by beta is greater than x bar minus x star, so obviously this quantity greater than 0. This, actually this is the derivative. So from this curve, when this 1 by beta, that from this point beta is less than this. So when beta lies in the left hand side of this, so the tangent at this point, actually tangent at this point is positive, at this point less than beta, beta cap. So at this point tangent is, this point tangent is positive, and for right hand side of this point, from this point, this tangent at this point is negative. So this tangent value is negative. So when beta is less than 1 by x bar minus x star, this first derivative is positive, and beta greater than this, that is if 1 by beta is this, then first derivative dd beta log of L1 is negative. From this diagram, we get this. So actually, clearly from this picture, this log beta function is maximized, globally maximized. Globally means this throughout the region globally. This maximized at this point. Beta, actually next we prove that this is the beta cap, say maximum likelihood point for this point, this beta, for this beta. So so log L1 to the base e, that is the L1 function, is globally maximum for beta equal to 1 by x bar minus x star. So L is also globally maximum for those values of alpha and beta. Hence, the required maximum likelihood estimates are given by alpha cap, alpha hat equal to x star, which is equal to the minimum of the sample values, is one answer. And other answer, beta hat equal to 1 by x bar minus x star, where we assume x bar not equal to x star, is maximum likelihood estimate. This is alpha cap. This is the minimum of all sample values xi. This is alpha cap for that point, alpha cap for alpha hat. This is the alpha hat is the um, maximum likelihood estimate for this alpha cap, which is x star. Is the minimum value of this, and beta hat is this. Now here we discuss for this, what is the maximum likelihood function estimation, MLE, is a primary statistical method for determining the optimal means maximal or minimal parameters is from the link with population parameters. Actually here parameters mean in statistics of a probability distribution based on observed data. It identifies the parameter values that make the observed data most probable under the assumed statistical model. So this is the maximum likelihood estimation. While the probability predicts future outcome based on fixed parameters, like likelihood evaluates how well different parameters values explain the data that has already been observed. Actually, uh, how maximum likelihood estimation is calculated? First, we select the distribution, mathematical distribution, either normal distribution or Poisson distribution or Bernoulli distribution, etc., etc. Define likelihood function, this L theta, and the joint probability density function of the data uh, as a function of parameter theta. Then taking log transformation for easier calculation, natural logarithm to the base e taken to create likelihood function, and this converts the product of the probabilities into simpler sums without changing the location of maximum. No change. So L and log L to the base e have the same maximum or minimum. Maximize solve for the parameter value where the derivative of the log likelihood is 0, that is peak. This is done, first order derivative equal to 0. This is done either analytically using calculus or numerically. Here we calculate analytically, analytically by the knowledge of calculus. And key properties of this MLE: consistency. As the sample size grows, the MLE converges towards the true value of the population parameter. Very important things. This MLE, maximal likelihood estimate, converges to the actual population parameter, which is unknown actually. Efficiency. Among unbiased estimators, the MLE often achieves the minimum possible variance for large data sets. Asymptotic normality. With a large enough sample, the distribution of MLE itself tends to follow a normal bell-shaped curve. And invariance, if theta hat is the MLE for theta, theta is the population parameter and theta hat is the MLE, maximum likelihood estimates of theta, then g of theta hat is the MLE for the transform parameter g theta. Thank you for observing this video.